Hello friends, welcome back to our channel Reds Info Hub. Yes, in this session we are going to discuss a new chapter, atoms, which comes in 12th physics. Okay, yeah, atoms. Just a second, I will see the adjustment of the camera. Okay, fine. Yeah, okay. Yes, everyone. Okay, yes. In this chapter, atoms, we are going to discuss about different atomic models. First, let us start with some brief uh, history. The first person who has given the idea of existence of atoms in matter is given by Democritus. Democritus is the first person who has given the idea of existence of atom. The idea of existence of existence of atom. Okay. As with the help of this idea, so different scientists have tried to explain uh, how to. They have just trying in different ways in explaining about the atoms, the existence of atoms. In that process, the first idea regarding the structure of atom was given by a scientist called J. J. Thomson. J. J. Thomson. So, this idea, as named as Thomson's atom model, this was later modified by Rutherford and later by Niels Bohr and then later by Sommerfeld, etc. Right? Let us see now what are these ideas which are named as atomic models based on the honor of their names, like Thomson's atom model, Rutherford atom model, Bohr atom model, etc. Let us see first who are contributed in explaining this structure of atom or atomic models. So the different atom models are, the first one, as we just have discussed, the first contribution has made by whom? As the first idea of structure of atom is given by whom? As Thomson. As everyone, let us now enter into the actual part of this atoms or atomic structure. So before that, just I would like to say everyone, myself, I'm Mr. Redepataniru. Welcome back again to our channel Reds Info Hub. If anyone not subscribed our channel, please subscribe the channel. Just I don't say some words that I don't ask for subscription and all. Yes, I will ask for subscription. Please subscribe the channel and click on the bell button so that whenever we upload the new videos, you will get the intimation immediately, notification immediately. Yes, let us enter here. Atom models or atomic models. Different atomic models. The different atomic models are, the first one, as we have discussed, as given by Thomson. Thomson's atom model. Atom model. This atom model is also called as plum pudding model. Plum pudding model, or or watermelon atom model or watermelon model. watermelon I hope this is visible. Yes, watermelon model, right? And the second one, actually, this was modified by the another scientist, is Rutherford. So we call it as Rutherford's model. Rutherford, Rutherford's atom model, which is also called as Rutherford's nuclear atom model or Rutherford's planetary atom model also, right? And the third one is Bohr's atom model. Bohr's atom model, and the next one is Sommerfeld's Sommerfeld's atom model, right? Whatever the flaws or drawbacks in all these atom models were covered by or rectified by one of the atom model called as vector atom model. Vector atom model. Okay, but in this chapter we are going to concentrate only on the first three atom models. What are these? And we are not going to touch these atom models. Is it okay? Right? Yes. Just note it down, everyone. Copy it down. If you need, just you can pause the screen and you can note it down. Got it? Or you can take a screenshot and you can go ahead. Right? Just I'm erasing this and let us see first briefly what is Thomson's atom model, then Rutherford's atom model, etc. So one by one. So first, what is Thomson's atom model? Actually, Thomson has given the first idea regarding the structure of atom. According to his idea, what his idea says is he has considered atom as a sphere, a solid sphere. Rutherford has considered the entire atom as a solid sphere in which the entire positive charge of the atom and its mass is distributed uniformly. Entire its mass and positive charge is distributed uniformly in this everywhere like this, and negative charges are embedded in this like seeds in watermelon. This is the idea given by Thomson. And with this idea, he has explained satisfactorily some experimental observations like ionization means emission of electron, right? So we can also say specifically thermionic emission, photoelectric emission, like this kind of experimental observations he has explained satisfactorily by using his idea. But he fails. He has failed in explaining some of the other experimental observations like alpha scattering experiment and origin of spectral lines in atomic spectra. That's why this atom model was it was actually it requires, that's why it is considered it requires some modifications to this atom model, but he did very great thing by initiating in explaining the structure of atom, right? That leads to further atom models, right? He has made the foundation and base for explaining what is the process of explaining the structure of atom model. So the next atom model, just here I am not going to dictate my many theory points over here. So just first point related to this is it has considered according to this, you can say according to this atom is a solid sphere with its entire positive charge, with its entire positive charge and mass is uniformly distributed uniformly distributed with negative charges embedded in this, with negative charges embedded in it, just like seeds in watermelon, like seeds in watermelon. So it is also called as watermelon model, or I can say, according to this, atom is a solid sphere in with its entire positive charge and mass is uniformly distributed with its negative charges embedded in it, like plums in a pud. Plums in a pud. So it is named as plum pudding model. Right? You might have seen plum pud cake. In that, like how the plums will be incorporated or you can say embedded. So just like that, negative charges. He has assumed that negative charges will be embedded in this in that fashion. That's why it is named as plum pudding model. Right? This is briefly about what is Thomson's model or atom model. And as I told, just if you want, just you can copy this. What is the idea given by Thomson? Then let me give you those points related to it, the drawbacks of this as well. Right? Copy it. Yes. Next, let us go ahead with the next part. That is, this has explained, as I told you, this atom model has explained satisfactorily some experiments or experimental results. That is, it explained satisfactorily, it explained satisfactorily the experiments, like the experimental observations, the experimental observations like thermionic emission. Okay, number one, thermionic emission, and number two, photoelectric emission, etc. Not etc. Like this kind of emission of electrons related experimental results, it has explained satisfactorily, but it failed. It failed in explaining alpha scattering experiment. Alpha scattering experiments means the results of alpha scattering experiment. It has failed to explain. It has failed in explaining alpha scattering experiment or experimental results of alpha scattering experiments or the observations made in alpha scattering experiments. And it has also failed in explaining, in say one alpha scattering experiment. There are even many other points, like what you say, many other what do you call advanced experiments or observations, like the stability of the atom was not like brought here. The origin of spectral lines. It was observed that spectrum is the characteristic of every atom, and these spectra are observed to be a line spectra, and this atomic model has failed in explaining the origin of. So how these spectra line spectra, it is failed. That is the origin of atomic spectra, right? And these shortcomings of this atomic model are somewhat, to some extent, satisfactorily explained by the modified atom model called Rutherford's atom model, right? So, but even Rutherford also has actually failed in explaining this particular part, what is the origin of atomic spectra, and that was that failure of even Rutherford atom model was overcome by are rectified by another atomic model called Bohr's atomic model. Let us see one by one. So these are few points related to Thomson's atom model. Is that clear, everyone? So Thomson is the first person who has given the idea of structure of atom, and according to his idea, atom as a whole is a solid sphere with its entire positive charge and mass is distributed uniformly, with negative charges are embedded in this like seeds in watermelon, right? With the help of this idea, he has explained satisfactorily thermionic emission, photoelectric emission kind of experimental results, but he has failed in explaining this. What is that? Alpha scattering experiment results and origin of atomic spectra, etc. Is that clear, everyone? Now, let us see what is Rutherford atom model and how he has explained the failures of this atomic model. Okay, are you ready? Yes, just you can, if you have already copied, it's okay. Otherwise, just you can pause the screen and copy out these points. Let us go ahead with the next model, Rutherford atom model. Yes, let's start. Next one is, write down everyone the subheading Rutherford's atom model. We can also call it as Rutherford's nuclear atom model or planetary atom model. Okay. The second one, Rutherford's atom model. So Rutherford actually to give the assumptions or idea of his atomic model. First, he has proposed one experiment to understand or to explain the structure of atom. So, what is that? Let us see here now. So, the next second one is Rutherford's atom model, which is also called as nuclear atom model. Nuclear atom model or planetary atom model. Okay. Yes. What is this nuclear atom model? Our Rutherford's atom model is, as I told you, to give his atom model, he has proposed an experiment called alpha scattering experiment. In the year 1906, he has proposed alpha scattering experiment. But in the year 1911, one of the undergraduate student in his lab who is working under the supervision of Geiger. So in the year 1911 is an undergraduate student called Marsden under the supervision of Geiger has come forward to perform this experiment. So Geiger has accepted and has brought this idea of performing experiment to Rutherford. By taking the consent of Rutherford, they have performed this experiment, and they have observed very interesting facts and what you call experimental results. These results have paved, we can say that, a strong base for the understanding structure of atom in the later course, you can say. What are the observations made by this experiment, and from those observations what they have concluded? We can call those conclusions, or we can also call them as results. What are the results of this experiment? Let us try to understand one by one. First, let us see what is the experimental setup made by these guys. The experimental setup. Then let us try to discuss about the experimental observations. Okay. First, write down the heading, subheading, alpha scattering experiment. Write down, everyone. Alpha scattering experiment. Alpha scattering experiment. Yes. What is the setup, experimental setup of this? Let us see first. Then we'll see what are the observations. Actually, they have considered one source of alpha particles. That source of alpha particles is, I think, is considered taken as bismuth. Bismuth. Here it is a source of alpha particles. Source of alpha particles is taken as bismuth. Is one of the radioactive elements. Usually, this we will study in the next chapter called nuclei chapter. What are radioactive elements and what are these what you call alpha particles, beta particles, gamma particles, are these radiations which are emitted by radioactive elements under natural radioactivity or what you call artificial radioactivity conditions, right? See, this bismuth, which is a radioactive element, when it is emitting alpha particles, these emitted alpha particles are made to travel in a straight lines like this. When this they will once it emits alpha particles, they may travel in all possible directions like this, a bunch. But to avoid traveling in all directions, they to made it is traveling in a particular direction, like a beam or a straight or narrow beam. They have used lead bricks. Lead bricks. These are lead bricks. These lead bricks made these alpha particles travel in straight lines. These are called lead bricks. Lead bricks, which are used to make the alpha particles to go in a narrow way. We can also call it to make the alpha particles to collimate. Collimate means to make narrow. And these collimated alpha particles or narrow alpha particles are allowed to fall on metal foil. Usually, this metal foil can be of any kind of copper foil or aluminum foil or even this some gold foil like that. Here, we are considering a gold foil. It is they are allowed to fall on a metal foil. It is a thin gold foil. Thin gold foil whose thickness is considered to be of the order of 10 to the power thickness. This thickness, thin gold foil of thickness 10 to the power minus 6 to 10 to the power minus 8 meters. 1 micrometers to 0.01 micrometers range. Right, when these alpha particles, these are alpha particles, when they're the what do you call they're moving means they're said to be having some energy. The energy of these alpha particles are said to be of the order of some around 5 MeV. MeV means million electron volts or mega electron volts to maximum possible energy of these alpha particles considered over here are 7.7 MeV of energetic alpha particles are allowed to fall on this metal foil. On falling this metal foil, they observed to be deviated from their path or scattered. So instead of traveling in this direction, they observed to be scattered from their path through some angle. This angle is called as angle of scattering or scattering angle. Angle of scattering or scattering angle. So these alpha particles, which are it is observed that some particles may pass undeviated and some particles may deviate or scatter through some angle theta. These particles are collected by using a detector, and for detecting purpose, a microscope is utilized. And actually, here to first of all to collect this, a screen is arranged here in circular shape. A circular shape screen is arranged. Just I might have drawn little down part, little more. Just you have to just draw a little carefully. That should be in a proper circular shape. Okay. So this actually is a circular screen. A screen in circular shape. This screen is made of zinc sulfide (ZnS). So the screen is made of zinc sulfide. It is a ZnS screen. Why ZnS zinc sulfide is considered here is once the alpha particles falls on this zinc sulfide, they will have a peculiar behavior of creating scintillations, means bright spots. That's why it has chosen over here. So on falling of this alpha particles on zinc sulfide screen, they create scintillations. Based on this, by observing the scintillations, they used to be detected with the help of these alpha particles. Used to be detected with the help of a screen. A detector. This detector, as I told you, detector is nothing but microscope. Microscope is using as a detector, but this detector is arranged in such a way that this can be movable through the circular path along this screen. So we call it as rotatable detector. Got it? So this is a rotatable detector. Also, you can call it as a movable detector. Rotatable or movable detector. So detector here, the role of detector is playing by microscope. Got it? So this scattered particles will be collected by using this detector, and this is how the scattering of alpha particles experiment is set up. This is the experimental setup. In this process, they have observed very interesting things. We can say that interesting observations are made. What are those observations, experimental observations? Let us see one by one. So first of all, just you can pause the screen and draw this experimental setup. The remaining this next, what observations they have made by using this setup? Let us see one by one. Very important observations. Okay, so copy it down, everyone. You can pause the screen and copy it. Otherwise, you can take a screenshot. Yes, as I hope done. Even the board is also clear. Entire board is covering. I hope. Yes, done. Yes, now, yeah. So now let us see what are the observations they have made. Important observations. So what they have observed is, once these alpha particles, incident alpha particles, once the alpha particles incident on the metal foil, that they are incidenting on the metal foil means, as it is a very thin metal foil, the metal will be having atoms, and hence it will be electrically neutral. It will be having some positive and negative charge. So it is observed that when the alpha particles falls on the foil means atom. Say if you consider this is the atom, this is the atom. It was observed that the detector is observing most of the particles are traveling in straight lines path or without any deviation, without any scattering. That means the first observation says that most of the alpha particles, most of the alpha particles travels undeviated or passes the metal foil without deviation or undeviated. Most of the alpha particles passes this metal foil undeviated, means without any scattering. So scattering, that is scattering angle theta will be equal to 0. So if this is the center of this, and if you draw a line passing through this, it is observed that many of the alpha particles passing over here, like here, somewhere this side out, this what do you call peripheries near the edge of this. It is observed that many of the alpha particles are traveling without scattering or without deviation. That is almost, here I would like to add one more point, that most of the alpha particles, here you can say most of the alpha particles, approximately 99.86% of incident alpha particles passes, right here. This I will add, this part of the board will not be visible. Passes the metal foil undeviated without any scattering. And it is also observed that observe that. Can take the second point. This is the first point. Second observation, it is they have observed that only about 0.14% of the incident alpha particles scatters at angles greater than 1 degree or deviates by an angle greater than 1 degree. Only about 0.14% of alpha particles scatters by angles greater than 1 degree. 1 degree, that is theta greater than 1 degree. Is that clear? So that means a few particles, only 0.14% of the particles, then when they're coming here, they scatter like this. That means they deviate slightly, or you can say 0.14% of the particles, they deviate by angles, or deviate or scatter by angles greater than 1 degree. Greater than 1 degree means it may be 10 degrees or 90 degrees or more than 90 degrees also. These many particles are undergoing scattering. Alright? In this, it is observed that one in about approximately, it is not like a fixed number, about 1 in 8,000 particles, 1 in 8,000 scatters or deviates by an angle greater than 90, scatters by theta greater than 90. What does it mean is, say a few like you can say that a few particles may deviate with slightly like this, got it? Whereas 1 in 8,000 have deviated by angles greater than 90 degrees. So vertical angle is 90. So more than 90, they are observed that 1 in 8,000 alpha particles scattered by an angle greater than 90. Even here also we can observe the same like this, right? One more very important observation they made here is approximately or about 1 in 10 power 6 alpha particles have undergone scattering by an angle of 180 degrees. 180 degrees. What is that 180 degrees means? 1 in 10 power 6 alpha particles means 10 power 5 is 1 lakh. 10 power 6 is 10 lakh particles. Out of 10 lakh particles, so many particles, if they come like a beam, somewhere one particle which is passing somewhere here, like passes through a line, and it is observed that it will reflect back or bounces back. That means then it undergoes an angle of scattering. About 1 in 10 power 6 alpha particles scatters by theta is equal to 180 degree, or 1 in 10 power 6 alpha particles bounces back along same line. So what might be the reason? So to explain this, they have utilized their leveraged different concepts, physics concepts. Let us see by using different concepts what they have concluded from these observations one by one. So note down these experimental observations made in alpha particle experiment carried out by Giger and Marsden. We also call this as Rutherford Giger Marsden alpha particle experiment also. Okay, so note down these points, everyone. Note down these. Let us see next. Based on these experimental observations, what are the conclusions drawn? What are the conclusions drawn? We also call the conclusions as the results. What are the results of alpha particle scattering experiments? Let us see one by one. Yes. Yeah. Just I'm erasing this. What are the results they have concluded from these observations? If you see from the first observation, let us see. It says that most of the alpha particles approximately of the order of 99.86% of incident alpha particles passes the metal foil undeviated. That means with theta equal to 0. From this, what they have concluded is most space of the atom, most space of the atom, the inside space of the atom is empty, nothing is there. So most part of the atom or most space of the atom is empty. So this is the conclusion they have drawn from the first observation, or we can call it the result of the first observation. So we can write down here conclusions of conclusions conclusions of conclusions or results of alpha scattering experiment. Conclusions or results of alpha scattering experiments. Try to draw neatly the conclusions or results of alpha scattering experiment. So note down what are the conclusions drawn, what are the result of this experiment. Results are, the first conclusion is they have understood that most space of the atom is empty. This is the conclusion they have drawn based on the observation, because about what? About 99.86% of alpha particles scatters at 0 degrees, right? Or about 99.86% of alpha particles passes undeviated. From this observation, they have concluded this result. Most space of the atom is empty. So these particles are moving undeviated. And the second conclusion or result of this alpha scattering experiment is from the second observation, that is about only 0.14% of alpha particles are scattering by an angle greater than 1 degree, right? That means alpha, here we have to just know one point. What is that? Is alpha particle is nothing but helium nucleus, W ionized helium nucleus, that is He24. So atomic number, this you can we'll again discuss about this nuclei representation in next chapter also. If you take this and you have studied this what you call atomic structure or all these atomic models in chemistry 11th standard also. So this is kind of revision for you guys. So I guess or I believe every one of you know these points, and this is kind of revision for you. And you can represent this as XZA, where Z is atomic number. So atomic number of protons is atomic number is nothing but number of protons. So it is said to be having is a doubly ionized, means neutral atom will have equal number of protons and equal number of electrons. Doubly ionized means 2 electrons have removed. It is having 2 protons and 2 electrons in neutral condition. If 2 electrons are removed, it will be said to be having only positive charge. So alpha particle is said to be positively charged nucleus or positively charged element. So when these positively charged particles are passing through the atom, they're deviated from this, means the similar kind of charge, as these are positively charged, similar kind of charge is presenting inside the atom, that is pushing them or repelling this alpha particle. That is what they have concluded, right? So as we know that already from your lower classes, we know that like particles repel and unlike particles will attract. From that concept, it is concluded that as alpha particles are deviating, means some similar kind of charge is there inside the atom, that is pushing this or making the alpha particles to deviate. That means positive charge is there inside. It is concluded that second conclusion or result is there is some positive charge. There is some positive charge inside the atom. This was the conclusion drawn from which observation? Because about 0.14% of alpha particles deviates by theta greater than 1 degree. Theta greater than 1 degree from this observation. About because about 1.14% of alpha particles, 0.14% deviates by theta greater than 1 degree. It was concluded that there is some positive charge, similar charge as that of alpha particles, called positive charge inside the atom. Got it? And from the third observation, that is around 1 in 8,000 deviated angles more than 90, that of course comes under this, and 1 in 10 power 6 deviates by 180 degrees angle, scatters by 180 degrees angle. From that, it is concluded that there is some huge, the strong force is acting on these alpha particles. Because of this, the alpha particles traveling towards the atom will slows down, even though they're traveling with some energy like around 5 million electron volt or 7.7 million electron volt. They will be stopped by huge opposing force. Then they will retrace back along the same line. Is that clear? So from that observation, it was concluded that there is huge value of positive charge is concentrating at a small portion at the center, that is named as nucleus. So Rutherford is credited with the discovery of nucleus. Till then, they were actually the scientific community, the people were not having the idea of nucleus. So he has coined the term called nucleus, the central core of the atom, where the entire positive charge of the atom is concentrated, is called nucleus. That term was actually introduced by Rutherford with the help of this experiment called alpha scattering experiment. That's why this is one of the very powerful experiments. Even still, it is taken into consideration in understanding some points regarding structure of atom. Right. So the next conclusion, before writing this, okay, note down these points. I will erase this and I will give you back. I will give you the remaining points. Yes, let me erase this. The next conclusion or result. The next conclusion or result of this alpha scattering experiment says that the entire positive charge, or most of the positive charge, or entire positive charge, the entire positive charge. Actually, the second conclusion says that there is some positive charge is there inside the atom, so that it is pushing this away or deviating the particles. But from the next observation, it is concluded that this entire positive charge is concentrated in a small space, in a small space at the center of the atom, which is called as nucleus, which is named as nucleus. This is the one of the very interesting conclusion drawn from these observations. Is this clear, everyone? How this is this result has concluded based on observation 1 in 10 power 6 alpha particles scatters by theta is equal to 180 degrees. Based on this observation, they have concluded this point. Right? These are very interesting conclusions they have drawn. Based on all these observations and conclusions, they have drawn one graphical relation which represents the relation between number of alpha particles scattered with respect to the angle of scattering. Let us see what that graphical relation gives us. So I hope you have copied this. I'm erasing it. Based on this results and observations, a graph is plotted between number of scattered alpha particles and the scattering angle. This graph looks like this. If you take n number of alpha particles scattered and theta angle of scattering, you can write down here what is n, what is theta. N is number of alpha particles scattered, and theta is scattering angle or angle of scattering. Are you following, everyone? So if by making use of this data observed in the experiment, the number of particles scattered by observing by what is that? The number of alpha particles collected by using the detector. If you plot here, it is by taking some calibration over here. This theta is 0, some 20, 40, 60. Let me draw a little bigger graph, little lengthier lines, so that you can accommodate the numbers here. 0, 20, 40, 60, 80, 100, 120, 140, 160, 180. This 180 theta will observe for 1 in is 1 million, right? So if this is n, you can take it as a 10 power as 0, right? Then 10 power 1, 10 power 2, 10 power 3, 10 power 4, 10 power 5, 10 power 6, 10 power 7, and different values of number of alpha particles scattered. It was observed that for at smaller angles, huge number of particles are traveling, number of particles scattered, passed are more at smaller angles, almost at zero angles, like and almost at zero angles, relatively huge number of particles are like scattered passing through the atom. And if the angle is increasing, less number of particles are scattering like this, some less number of particles, same somewhere here like this. So these dots, if you consider as experimental data, then by using one of the theoretical relation, this the graph has fitted as a line like this. If the solid line is a theoretical line given by a theoretical equation taken by Rutherford's team. Okay, this theoretical curve or solid curve is drawn by using one of the theoretical equation. What is that equation? This I will give you just for an idea, and we are not discussing how to derive that equation or how to get that equation. Based on these observations only, he has proposed one theoretical relation to fit this graphical representation. What that theoretical relation says is, or gives, this theoretical relation gives number of alpha particles scattered is given by this. N is number of alpha particles scattered is given by n is equal to capital Q small n t z square e power 4 divided by 8 pi epsilon naught whole square into r square e square sine power 4 theta by 2. This is the theoretical relation given by Rutherford's team in explaining what do you call number of in explaining the theoretical fit of this graphical relation, right? where this n gives the number of particles scattered. Well, what are these parameters? Just for understanding purpose, I will give you one by one what is what. Where capital Q is the total number of alpha particles incident on the metal foil. The total number of alpha particles incident on the metal foil. Just a second. Yeah. Q is total number of alpha particles incident where on the metal foil, whereas small n number of atoms per unit volume in the foil or sheet, whereas T is right. I hope this is visible, right? As well as the T is thickness of the sheet or metal foil, thickness of the foil, and Z is atomic number of atoms of the foil means with what atoms the foil is made of, what element the foil is made of, whether it is a copper foil or gold foil, what atoms it is comprising of, right? And E is elementary charge, or we can say magnitude of charge of proton or electron is nothing but elementary charge, and R is the distance between the foil and the screen, the zinc sulfide screen. Distance between foil and screen. Got it? Is R, and E is kinetic energy with which alpha particles are moving. E is kinetic energy, right? R is clear. So I think this part is not visible. So let me write down this over here. Yeah, where E is kinetic energy of all incident alpha particles. Right? And what is this? In this sine power 4 theta by 2, theta is angle of scattering. Right? I hope these terms are clear for you. As I told you, this is the theoretical relation provided by Rutherford to fit this experimental data in this graphical relation, right? And based on this, he has also given one more relation that the number of alpha particles scattered at a particular angle of scattering is depending on the nature of the element or nature of the metal sheet. By fixing all other parameters constant, means energy of the particle, distance between the foil and the screen, thickness of the screen, and all these parameters, by fixing, it is a relation is given that number of alpha particles scattered depends on the element that is given by Z for fixed theta. So this further can be expressed as is equal to some k, constant k into Z square by sine power 4 theta by 2. By making use of this, you may come across some numericals also. So while doing that, while doing the numericals, you have to make use of this relation. Is that clear, everyone? Yes, note it down. Next, so here, just a minute, let me conclude this part of the discussion. What is that? Alpha scattering experiment, observations and conclusions. Observations, first experimental setup. I hope every part of the experimental setup is clear for you guys. And from the experiment, it is observed that quickly most of the alpha particles are passing undeviated without any scattering, that is at scattering angle of theta equal to 0, and only about 0.14, that is most of the alpha particles, means around 9.86% of incident alpha particles are passing undeviated, and Only about 0.14% of alpha particles, about approximately, are scattering at angles greater than 1 degree. And it is also observed that about 1 in 8,000 alpha particles are scattered by angles greater than 90 degrees, and 1 in 10 power 6 alpha particles are scattered by an angle theta equal to 180, means they bounces back. So from these observations, it is concluded that, right, most space of the atom is empty, and second conclusion they have concluded is some positive charge is residing inside the atom, and third conclusion, a result of this experiment is the entire positive charge is, of course, it is residing inside, means where it is concluded that it is entire positive charge is residing at a small point, small space that is the space is called as nucleus, and the entire positive charge is concentrating at the center, a small space at the center, which is called as nucleus. Alright, and one more point based on this, because this theoretical fit is in agreement with the observation. So from this, it is concluded that the number of alpha particles scattered at a particular angle of scattering is depending on the element. For different elements, different number of alpha particles are scattering at a particular angle of scattering. So these are the conclusions given by alpha scattering experiment. I hope you guys have understood all these points. So note it down. Let us go ahead with the remaining part of what you call this alpha scattering experiment. It's experiment only. Yes. Have you copied? Pause the screen and copy it. Yes, the next part, the next continuation part of this is, it was also observed from this experiment that if you consider alpha particles are incidenting on atom, if you consider here, this is energy of alpha particles. Energy of alpha particle, which is having some mass and moving with velocity v, the energy of an alpha particle is given as V is equal to kinetic energy half mv square. Where velocity, v is velocity of the alpha particles, right? So based on that point, based on this quantity, velocity, direction, they have introduced one more point here. What is that? Let us see. So what they have understood, one more point related to this experiment is what they have concluded or observed based on some observation. They have concluded is, let us see. It is observed that when alpha particles are traveling, let's say, let's draw once again this atom. So this is a line passing through the center. This is center of nucleus. If an alpha particle is moving over here, it may pass as undeviated. It is moving over here, it may pass as undeviated. Are following carefully? Whereas if it is passing little closer by, it may pass by, may deviate by smaller angles. But little closer, they may deviate by angles greater than 90 degree, right? Like somewhere here, they deviate at lesser angles. Little closer, they deviate by more than 90. And if they are passing along this line, they will stop and bounces back. From this, what they have proposed is, if you consider the direction of initial velocity is this v, then this is the nucleus. The perpendicular distance between the direction of initial velocity and from the nucleus is given a special name called impact parameter. What is impact parameter here? Now write down this subheading: impact parameter. Impact parameter. It is denoted by small b. What is impact parameter? Impact parameter is nothing but the perpendicular distance between the velocity direction, initial velocity direction from the nucleus. The perpendicular distance between initial velocity direction from the nucleus is called impact parameter. impact parameter, right? This impact parameter is related with angle of scattering. So that briefly I'm giving, not this I'm not giving the mathematical relations and all here. So this is observed that this impact, if this is the position of alpha particle, impact parameter is this. If this is position of alpha particle, impact parameter is this. So impact parameter will be different for different alpha particles here. If impact parameter is a small, angle of scattering will be large. You're getting? Even for when it is lying on this, impact parameter is 0. So angle of scattering is 180. It is bouncing back 180. B is 0. If B is 0, theta is equal to 180. If B is 0 means it is falling along the same line. The line passing through center of the nucleus. Whereas if B is greater than 0, so that if it is having small value, but provided it is nearby, closer to the nucleus. If it is closer to the nucleus, then theta will be more than 90. So it is less than 180. If B is increases, theta is decreasing. And if it is somewhere here, far away from the line passing through center, somewhere here, it passes undeviated. That means for larger value of B, theta will be equal to 0 if B is much greater than 0. Got it? That means these two are inversely proportional. B increases, theta will decreases. Only this relation I'm giving here. There is some mathematical relation between them. That part, like I don't want to give at this point. Okay. This is briefly about. This is what is briefly about impact parameter. Here, better you write down the definition of impact parameter. Write down. Impact parameter can be defined as the perpendicular distance between. Write down the perpendicular distance between initial velocity direction, the perpendicular distance between initial velocity direction and the nucleus, the perpendicular distance between initial velocity direction and the nucleus, is called impact parameter. Alright, just you can mention here, you can note down this. This will give brief idea about what is impact parameter and what is the relation between impact parameter and angle of scattering. Just note down these points also. Okay, yes. This is the simple conceptual point you need to have an idea about. Next, very important concept here you need to have an idea about is distance of closest approach related to this. So just you can pause it and you can note down, or you can take a screenshot of this. Yeah, let us go ahead now with the next concept called distance of closest approach. A very important concept in this case, and that indeed has given an idea of calculation of size of nucleus. Okay, that has led to the discovery of nucleus. Okay, yeah. See, what is the distance of closest approach? Closest distance of approach. Distance of closest approach. Closest approach. Name itself tells about that. So it is denoted by R naught. What is this? Again, the same diagram you have to consider here. So let us see. Let us consider the atom. Draw that one. The same circular structure or spherical structure of the atom. Yeah, see here. If you consider this is the spherical structure of the atom, when what do you call alpha particles, a bunch of so many alpha particles comes here, 1 in 10 power 6 alpha particles, and when it is passing through a line which is passing through the center of, what? The nucleus, which is passing through the center of the atom. What is that? If 1 in 10 power 6 alpha particles, that alpha particle, when it is passing through center of the atom, it experiences huge repulsive force. That repulsive force is provided by electrostatic force of repulsion between the alpha particle and nucleus, which is supposed to be positive charge. So positive charges will repel each other, right? If an alpha particle is traveling, if an alpha particle is traveling with a large energy, with a large velocity, having a specific mass, so the energy will be, kinetic energy is half mv square. Like when it is traveling with huge velocity and with huge energy, zoom like this, as it approaches the nucleus, at the nucleus or center of the atom, the velocity will decreases because it is opposing force is increase, like when it is approaching, the opposing force will increases. As a result, the zoom velocity will come zoom stop. It will stop momentarily after reaching particular point, right, somewhere here. Then what happens is, still it is opposing with a strong force, so because of that it will bounces back along the same line. In this process, the particle, the zoom motion, so the what kind of what do you call, so the distance, when it comes here in this motion, when it comes and stops somewhere here after approaching the nucleus, this is the closest point it can approach the nucleus. Beyond that it cannot travel. This point, if you mark, and the distance of this point from the center of the nucleus will be called as distance of closest approach. It is marked as R naught. Correct? So what is, how can you just define, how to give a definition of this? What is this? It is the distance between what, the closest approach of alpha particle from the nucleus. Closest approach, it can approach the nucleus till certain this extent only. Beyond this it cannot. So the distance between the closest approach of alpha particle and the nucleus. Distance between the closest approach of alpha particle and nucleus is called distance of closest approach. It is denoted by R naught. Is it clear? And how to find this distance? So for this, and as I told you, this is one of the very important concepts in this Rutherford atom model. Let us see how to derive this expression. This derivation we will discuss about. So to derive that, we have to consider initially alpha particle is traveling from relatively infinite distance, where the potential energy, initial potential energy is 0. As it is having some mass and moving with some kinetic energy, it is said to be having some initial kinetic energy. Ki is equal to, you can write it as Ke, initial kinetic energy. While after reaching this, as it is traveling, like zoom, stop. When it stops, velocity becomes 0, kinetic energy also becomes 0. So here, this if we consider as a final point, at this point, final kinetic energy becomes 0. But because it is in, why it stops? Because of the repulsive force due to the nucleus. So there will be an electrostatic interaction between them. So because of this, you can say this entire kinetic energy which was having here converts into potential energy here, final potential energy. What is that potential energy? Let us see. And you can say that here the entire kinetic energy is converted into potential energy, and vice versa. Again, when it is coming back, it converts again back to kinetic energy and so on. So in this, conservation of energy is satisfying, or the law of conservation of energy is hold good in this process. So according to law of conservation of energy, so total initial energy is equal to total final energy. Total initial mechanical energy is equal to total final mechanical energy. It is nothing but sum of potential and kinetic energies. So that is it. Initial potential energy plus initial kinetic energy is equal to final potential energy plus final kinetic energy. Is this clear? Now, here initial potential energy is 0. Kinetic energy is, let us take it as Ke of mv square. You can take, otherwise you can take Ke is equal to final kinetic energy is 0, but potential energy here between these two is, let us say it is a first charge Q1, this is charge Q2. Charge of alpha particle is nothing but 2 times charge of protons, right? Whereas charge of nucleus is Q2 is equal to, if it is having Z, any nucleus will be made of any element, right? If it is gold sheet, it will be having atomic number of gold. If it is copper sheet, atomic number of copper you have to consider. It is equal to Ze, charge of this nucleus is nothing but atomic number of the atoms of the sheet into charge of elementary particle Ze. So by distance between them is R naught. By taking this into consideration, you can take UF is K is 1 by 4 pi epsilon naught. So K Q1 Q2 is 2E into ZE becomes 2ZE square. By distance between them is R naught. Directly have mentioned this. I hope you have understood. Otherwise, you can write down here UF is equal to 1 by 4 pi epsilon naught into Q1 Q2 by R. This is R naught. This you can take it as K. So here I have written it as K. Q1 is 2E into Q2 is ZE by R naught. So by simplifying this, what you can take K into 2ZE square by R naught. K into 2ZE square by R naught. On simplifying further, what do you want? R naught you want, right? Take it here, then you will get R naught is equal to, can keep if you want K as it is here itself. Otherwise, this K you can replace it 1 by 4 pi epsilon naught. So you can write it as 2ZE square by 4 pi epsilon naught into KE is the expression for distance of closest approach. So here it is observe that it is inversely proportional to kinetic energy, right? Directly proportional to atomic number of the atoms of the foil. So this is how we will get the expression for distance of closest approach. So we will do some numericals based on this maybe in the next session. Okay, and some of the experimental observations this has not able to explain also we'll see. Okay, so have a note of this. Have a note of this. This is the expression for distance of closest approach. Distance of closest approach. Fine. Yeah. Next. Let us see some numericals. Okay, before working out the numericals based on these relations, let us discuss about one concept, that is what are the experimental observations this atomic model has not able to explain. We call it as drawbacks of Rutherford's atom model or failures of Rutherford's atom model. Then we can work out the numericals. Fine. Yes. So, now let us look into the next concept: drawbacks of Rutherford's atom model. Note down subheading. Write down drawbacks or failures. Drawbacks or failures of Rutherford's atom model. Yes. So what are the drawbacks? Drawbacks or failures of Rutherford's atom model. So actually Rutherford's atom model has failed to explain one of the very important concept is stability of the atom. So Rutherford's atom model failed. It failed to explain the stability of the atom. Explain the stability of the atom. What is this? Let us see briefly. What is the failure of this is according to, so here this you may get like this, you need to have an idea about what is this. Sometimes you may be in conceptual based questions in need point of view also you may get some questions related to this. Okay, according to according to classical electrodynamic theory, classical electrodynamic dynamic theory, any charged particle which is in accelerated motion or any accelerated charged particle radiates energy continuously. Radiates energy continuously. So according to classical electromagnetic theory, any accelerated charged particle radiates energy. Here, as electron is considered as it is revolving around the nucleus. Remember one point. This point is not proposed by Rutherford. It is according to some other theories. Based on those theories, they said that. So according to some other theories, this is how atomic structure is. But this was not explained by Rutherford. They have that is how they have mentioned this drawback. That is how they have brought this drawback or failure. Okay. But Rutherford has never said that electrons will revolve around the nucleus. From some other theories, it was that this point has brought. So according to those, electron is supposed to be revolving around the nucleus in circular orbits. As it is in circular motion, it is a charged particle. It is said to be in accelerated motion. As the charged particle is in accelerated motion, according to electrodynamic theory, classical electrodynamic theory, it has to radiate energy continuously. As it is having some energy and it is radiating, means it is giving energy continuously, it will lose its energy. So initially it will be having so much of energy, it will be like doing the rounds around the nucleus. As it is giving the energy, and energy will decrease. It will do the rounds like this with so much of less energy. With less energy, as it is still continuously, it is radiating energy. As energy decreases and going on, finally energy will completely goes off. It will do the rounds like this, and it may falls finally, ultimately onto the nucleus, and the atom will collapse. But it is not happening. What is not happening? The collapse of the atom is not happening. According to classical electrodynamic theory, any accelerated charged particle has to radiate energy. So here, electron is supposed to be, as when electron is considered as moving around the nucleus in circular orbit, it is supposed to lose energy. As it is losing the energy, it is supposed to move in circular orbits of gradually decreasing radius, then it has to fall into the nucleus. But it is not happening. Atom is stable. Why or how it is stable is not explained by what you call Rutherford's atom model. That's why it is taken as one of the drawback of this atom model. Okay, is it clear? So according to classical electrodynamic theory, any accelerated charged particle radiates energy, and here when as electron is in circular motion around the nucleus, it is said to be losing its energy continuously. Radiating energy means losing energy. Electron is in circular motion around the nucleus. It is supposed to radiate energy continuously, and undergoes gradually decreasing circular path, and undergoes gradually decreasing radius, undergoes a circular path of gradually decreasing radius gradually decreasing radius, undergoes a circular motion, in gradually decreasing radius. Okay, and ultimately falls into the nucleus, and hence the atom should collapse, falls into the nucleus, but it is not happening. But falls into the nucleus and atom will collapse, but it is not happening. But it is not happening. Okay, and it is not happening. Atom is stable. It is not explained by Rutherford's atom model. That's why it is treated or considered as the drawback of what you call Rutherford's atom model. Got it? And the second drawback. So note down this briefly. Just for understanding purpose, I have given the explanation about this why it is so. Just main point you have to consider is it failed to explain the stability of atom. That is the main point you have to just have a note of it. The second drawback of this is second drawback of Rutherford's atom model is even this atom model also not explained the spectral origin of spectral lines. Just like Thomson's model, this atom model also has not explained the origin of spectral atomic spectrum. It does not explain the discrete nature of atomic spectrum. Discrete nature means the line spectrum of atomic spectrum. Discrete does not explain discrete nature of atomic spectrum. Atomic spectrum. What does this mean is, according to this condition or according to this assumption, the electron is radiating energy continuously. It has to give, if you take a spectrum, it has to give a continuous spectrum. But experimentally we are getting discrete spectrum. Discrete means like line spectrum, not continuous spectrum. So this was not able to explain why this discrete nature of the atomic spectra is observed, right? And one more point related to this itself is why the atoms will absorb or emit radiations of a specific or particular wavelength or frequency. When, say for example, if you take any gas, and if you passes some white light through it, it was observed that the gas will absorb some wavelengths and it gives only few other wavelengths, so we get absorption spectra. The wavelengths which are absent in this, so the wavelengths which are absorbed by these atoms will absent in the spectrum, so those will be observed as dark lines in the bright background, right? So here the atoms will absorb only particular wavelengths. Why it is happening, it has not explained. So it does not explain why atoms absorb or emit light of only certain specific wavelengths. It absorbs or emit light of only certain specific wavelengths or frequencies. So this part is also treated as one of the failure of what we call Rutherford's atom model. So briefly speaking, these are the failures or drawbacks of Rutherford's atom model. It has failed to explain the stability of atom, and it does not explain the discrete nature of atomic spectrum, and it doesn't explain why atoms absorb or emit light of only certain specific discrete wavelengths. Right. So this is briefly about the drawbacks or failures of atomic, what is that, Rutherford's atom model, right? So here just I will take some time and let us work out few numericals, then I will wind up the session. Okay, done. Just copy these points, everyone. These are also very important points related to Rutherford's atom model. Based on this, you may get direct objective questions in NEET point of view, also NEET and JEE point of view. Okay, I hope every one of you know that these days the objective questions in JEE and NEET point of view are giving based on direct conceptual points. So you need to have an idea about a very conceptual point, especially what are the experimental observations, experimental results, or drawbacks. This kind of conceptual points also you need to have an idea about. So copy out down these points. Let us work out some numericals now. Okay. Yes, guys. As this session is taking a little more time, let me discuss the numericals in the next video. Just I'm winding up this. I'm stopping this session. Okay, take care, everyone. And if you have any doubts, you can, if you need anything or if any point is not clear, you can post in the comments. Okay. And if you like this, just the concept, you can press on like and subscribe it, and press on bell button also, so that you will get the notifications immediately after when you post the videos. Okay, take care, everyone. Yes, bye bye. Take care, everyone. Stay home, stay safe.